Hi there, we're going to talk about how to find eigenvalues and eigenvectors for a given matrix. Let's first start with the definition of an eigenvalue. So lambda is an eigenvalue for matrix A, and x is the corresponding eigenvector for A if A times x equals lambda x. The way we find this is taking the determinant of A minus I lambda and setting it equal to 0. That's how we find our eigenvalues. From there, we'll talk about how to find our eigenvectors. So in this case, we're going to look at this matrix, -3, -2, 10, 6. I had my value switched around. And the first thing we're going to do is find the determinant of A minus I lambda. I is the identity matrix, so I for a 2 by 2 equals 1, 0, 0, 1. So I lambda equals lambda 0, 0, lambda. Here is A minus I lambda. We're taking the determinant of that. What we get here is -3 minus lambda times 6 minus lambda minus -2 times 10. When we distribute that, so I'm going to do that. What we get here is lambda squared minus 3 lambda minus 18. And then on this side, this simplifies to positive 20. So just combining like terms, all we have here is lambda squared minus 3 lambda plus 2. And again, we're setting that equal to 0 to find the value of lambda, so equals 0. So we have a degree 2 polynomial. The way we solve that is by factoring. This factors to lambda minus 2 times lambda minus 1. Again, that's equal to 0, so lambda equals 2 and 1, both positive. Going over to the next board. Again, we want to find our eigenvectors now. So board 1 tells us our eigenvalues are 2 and 1. So to find our eigenvectors, what we're going to do is substitute each of those in one at a time and then solve a system of equations. The system that we're solving is A minus I lambda times x equals 0. Our goal is to find x. We know A, we know the value of lambda. We just need to find our x. So what we're doing here for lambda equals 2 is A minus I lambda. So -3 minus 2 is -5, -2, 10, and then 6 minus 2 is 4. So what we're doing here is solving this. Keep in mind x is a vector. In this case, it's a 2 by 2 vector. So x looks like x1, x2, vertical vector. And we're going to set this equal to 0. So what we can do here is row reduce this and solve for x1 and x2. We should see that every single time we try to find an eigenvector, we will have at least one free variable. So what we'll do here is, again, we're just going to row reduce this matrix, -5, -2, 10, 4. What I'm going to do is 2 row 1 plus row 2. And I'm going to put that back into row 2. What I'll have left is -5, -2. Well, row 1 times 2 is -10, -4. When I add that to 10, 4, I get 0, 0. And again, we're setting this equal to 0. We have a free variable. In my second column, I do not have a pivot position, which means x2 is my free variable. So we can say let x2 equal a. We want to make sure we know what a is. A is just some real number. So if x2 equals a, this first row says -5 x2 minus 2 x3. I'm sorry. -5 x1 minus 2 x2 equals 0. That's what that first row says. The second row just says 0 plus 0 equals 0. Well, I know that my x2 equals a, so I'm just going to substitute that in. So negative 5x2 minus 2a equals 0. Solve for x2. x2 equals negative 2a over 5. So what we have here is a vector. So the vector x equals 2a over 5 and a. So a can be any real number. We want it to be a non-zero vector, so our eigenvectors must be non-zero. Otherwise, we'll see that we have issues if we let our eigenvectors be zero vectors. That doesn't mean that we can't have a zero in one of the positions, but it just means that the zero vector is where we have zero in all positions. We cannot have that as an eigenvector. So what I'm going to do is pick a value for a. I'm going to pick 5 just because that'll help me get rid of that divided by 5. So then I'm going to say now let a equal 5. So our eigenvector for lambda equals 2, so I'm going to call that x sub lambda equals 2, is 2, 5. Again, we're just plugging in 5 for a. The top simplifies to 2, and the bottom is just 5. So our eigenvector for the eigenvalue 2 is 2, 5. We're going to do the same thing for lambda equals 1, and that's how you find your eigenvectors for corresponding eigenvalues.